Welcome to this evening's edition of Shield Instructional Videos. This video is on rotational motion, and this is the first video of this unit. The objectives of this video. First, we are going to look at how we measure rotating objects in physics. And then, we're going to use modified kinematic equations to solve for various quantities while we are rotating. So, as we talked about in class, what we have been studying thus far in physics is what we call translational motion, but there's also rotational motion. We also use different words. Sometimes people will call it linear and angular because everything we've done in this class has pretty much been moving in a straight line. The only exception to that would be when we did orbital mechanics. So everything up until now, with the exception of orbits, has been linear. And we've just been moving in a straight line, just kind of like the little green cars on your momentum labs, okay? So we're just looking at cars that have a velocity or are just moving in a straight line, and that's called linear motion. But sometimes, you know, on my weekends, I go out and I DJ at the club, and I'm dropping some beats, and so I, put my record on there and on the turntable, and it starts spinning with a certain angular velocity. And so we need a whole new set of equations and a whole new paradigm physics model to look at rotational motion. So we have this issue of we know what the linear side looks like, and now we are moving to this is what the angular side looks like. And so in class, I had you translate equations from linear to angular with these new symbols. So this video is going to go more into depth of what each of these symbols mean and how we find them and what their units are. So our first measurement of how we measure rotating motion is called angular displacement. And we use the symbol theta, which is a Greek letter for the th sound. So theta is what we use to measure angular displacement, and no, the symbol is not a zero, although sometimes you do see an O with a slash mark to mean a zero, but this is not a zero. Okay, so angular displacement. First of all, angular displacement is simply just the angle that an object rotates through. So for example, if you have a circle, and let's say I put a little blue dot there to represent where I want to see how the circle is moving, so I paint a little blue dot so I can see the circle actually moving. So let's say at time equals 0, the blue dot is there, and then 1 second later, it's there. Okay, so this angle right here that the blue dot has moved through, that is the angular displacement, and that is what theta is the angle that the little blue dot has traveled through. Okay. We measure angular displacement either two ways. One is in the units of radians, which the other video talked about radians. If you aren't in trig right now and taking or learning about radians. The other way we can measure angular displacement is through just degrees, which is kind of basically the two most common ways of measuring angle. So here's an example. Let's say I have a flat surface and I have a purple ball that I place on the surface, and just again so I know how the ball is moving, I paint a red dot on the bottom of the ball, okay, and I give the ball a little push. Okay, that would be linear motion, right? But while I give it a push, the ball actually begins to spin and rotate, and a while later the dot has come halfway up and now the dot's on the top, and then even further along the dot swings back down full circle to the bottom. Okay, so the question is, what is theta? What is the angular displacement that this object has gone through? Well, so the red dot helps us kind of track the motion. And so the red dot has gone from the bottom all the way to the top and all the way back down to the bottom. So that means that little red dot has traveled 360 degrees. Or if you're going to use the second way to measure it, it would have gone through 2 pi radians. And that would be the angular displacement. Okay? An even more interesting question would be, because this is a rolling ball, it would be, how far has the ball actually traveled? Okay, well, if you think about it, because the ball is rotating on the outside, That means that the distance it's traveled is equal to one whole circumference of the circle, because as the ball rotates, it covers every single surface of that ball. And so that means that the distance it's traveled is just the circumference of that ball or that hoop or that disc or whatever it is. And if you recall from geometry, the circumference of a circle is 2 pi times the radius of that circle. So hopefully you see that there's a connection, because both of those, there's two examples where you have 2 pi. So the angle in radians is actually 2 pi, and the distance it travels is 2 pi times the radius. So that leads us to the equation that the distance it travels, x, is equal to the angular displacement times the radius of the circle. But that only works if theta is in radians, because if you measure theta in degrees, then you would do 360 times r, which isn't going to work. It's only if theta is in radians that this equation works. And so again, this is important for us because this is how we're going to use, or how we're going to figure out how far things have traveled if an object is rotating and rolling at the same time, or just if we want to know the distance that it's traveled around the circle. This is how we go from linear to angular motion. And you'll recognize this equation if you are really smart, that this is the same equation as an arc length from geometry, except they use s, and so it would be s equals, say, theta times r. Okay, so moving on. Our second quantity that we use to measure circular motion or rotating motion is called angular velocity, which we use a lowercase omega. And no, that is not a but, even though it does kind of look like one. So angular velocity, it is the rate that the angular displacement, or the angle, is changing. Okay, so it's just like speed or velocity is the rate at which your distance is changing. This is the rate that the angle is changing. So again, if I have a circle and I put a little dot on the circle so I know how it's moving, okay, let's say that I move from this point to this point, and it takes me 1 second to move from that point to that point. Okay, that would require an angular velocity. There's a rate that I'm changing that angle. Okay, and we measure that in either RPM, which stands for revolutions per minute. So basically, how many times does the circle spin? How many revolutions does it take per minute? That's not as common in physics, but it's very common in physics applications, especially in engineering. You see RPM a lot. But we, in physics, will measure it in radians per second. That's much more useful for us, and we don't have to convert as much. So if I actually wanted to calculate the angular velocity of this object, I would divide how many radians I traveled divided by the time it took me to actually travel that. So in this case, I traveled pi radians, because it's half of a circle, in 1 second. So that would be 3.14 radians per second if you wanted to remove the symbol pi. And so just like distance, okay, if we want to go from velocity to angular displacement, or to angular velocity, then just like velocity, the equation that we use is v equals omega times r, and that's on your cheat sheet that I gave you earlier. And remember, velocity must be in radians per second, otherwise this doesn't work. Okay, another thing about angular velocity is sine. If my circle is spinning counterclockwise, then the convention is to have it be a positive angular velocity. Whereas if I'm moving counterclockwise, the convention is to have a negative angular velocity. And that's primarily based on the way that we measure angle, because usually we start out like over here as 0, and then we say this is positive 90. But if I started out here at 0 and I went down, we would call that negative 90. So that means turning clockwise is going in the negative direction, counterclockwise is the positive direction. But you, in your problem, get to define, your frame of reference. So you technically get to pick which way is positive and negative, but the standard is that counterclockwise is positive and clockwise is negative, just like running forward is usually positive and running backwards is usually negative. Okay, our third and final quantity is called angular acceleration, and we use the Greek letter alpha. And no, it's not a fish. Everybody likes to call it a fish, but it's not a fish. It's alpha. Okay, so angular acceleration, okay, is just pretty much like linear acceleration, but with circles or spinning objects. So it's the rate of change in angular velocity, just like normal acceleration is the rate of change of your normal velocity. So hopefully you see that they're pretty much the same thing. It's just spinning now instead of moving in a straight line. Okay, so if I have let's say I have a circle or like a disc and it's spinning, and right now it's spinning at 1 radian per second. Okay, and that's at time equals 0. And then, okay, let's say then I like push on it, okay, and I apply an angular acceleration to it. And that's going to speed it up because then 1 second later, it's now going 5 radians per second. So it's spinning a lot faster. Okay, that means that it went through an angular acceleration because it sped up. So speeding up or slowing down in spinning is caused by an angular acceleration. And of course, we measure this in radians per second squared, just like regular acceleration is meters per second squared. And again, just like velocity, if you want to go from linear acceleration to angular acceleration, the equation is that A equals alpha times r. So hopefully you see a pattern that if you want to go from angular back to linear, you just multiply the quantity by the radius. Again, though, it has to be in radians. Like all your quantities have to be in rads per second or rads per second squared, not in degrees. Okay, so on Friday, I had you guys look at all the rotational kinematic equations and kind of come up with them. Okay, so now we're actually going to look at and apply them. Okay, so our old 3 kinematic equations look like this revamped. We have theta equals theta naught plus omega naught t plus 1/2 alpha times time squared. We also have that the final omega, or angular velocity, equals the initial angular velocity plus alpha t. And then we have that omega final squared equals omega initial squared plus 2 times alpha times your change in angle, or change in theta. So I wanted to give you a couple examples to actually see these in action, okay, before class. So example 1, let's say I put in a CD player, or CD into my CD player, and it starts spinning, okay? That means that it underwent an angular acceleration because it wasn't spinning when I had it. I put it in, and now it starts spinning, okay? So let's say that that took 2 seconds to get up to that speed of 5 rads per second. I want to know what the alpha is, what the angular acceleration is. So in my head, I'm thinking, okay, well, I know that when I put it in, it wasn't spinning. So I know the initial angular velocity was 0. So that means that my 5 rads per second is a final angular velocity. And the only equation that I can think of that has all of those is that the omega final equals omega initial plus AT. And so when I plug in numbers, I get 5 equals 0 plus alpha times 2, which is really easy. Alpha is 2.5 rads per second squared. Okay, so that was a pretty easy problem, but I want you to see that it works just like our old kinematic problems. It's nothing really new. The only thing new is that we're spinning and you just have to grapple with these new terms and these new symbols, but it's all the same physics, really. Okay, so our second example is a little bit trickier, a little bit harder than the first one. Okay, so let's say a bike wheel is constantly rotating at 6.2 rads per second for a 30-minute ride. I want to know how far did the bike actually travel. Okay, so I hop on my bike, I go for a 30-minute ride, and I know that I'm going at 6.2 rads per second, or that's the angular velocity of the wheel for the entire ride. Okay, and so let's say that I know that my bike wheel has a radius of 20 centimeters, which would be 0.2 meters. Okay, so and I'm rotating at 6.2 rads per second, and it takes me 1,800 seconds because I converted 30 minutes to seconds. That would be 1,800. Okay, so I'm thinking to myself, well, I know that in linear, velocity is distance over time. So in angular, the angular velocity is the angle over time. Okay, so that means the angle is just the velocity times the time. So my angle is 6.2 times 1,800 seconds. And so that means I get an angle of, let's see, what is that? 11,160 radians. So that's how many radians this wheel actually turned. Okay, which is quite a bit. Okay, so the question then is that if I know how far or how much this rotated, can I use that to figure out how far I actually traveled? Okay, and so then think back to that first example I showed you where like a little wheel is spinning, okay, on flat surface. I can actually find out because I know that x equals to the radius times the angle in radians. So that means it's actually a fairly simple calculation. So 0.2 is my radius, and then I'm going to multiply that times 11,160 radians, and I get 2,232 meters, which is the equivalent of 2.232 kilometers, which is, I mean, that's like a pretty leisurely pace. I mean, that's about it's about close to a mile. So it means I'm biked a mile in 30 minutes, which is not super impressive. I need to step up my game. Okay, so to recap, in this video we talked about rotation. We said that rotation uses these new symbols, theta, omega, and alpha, to describe motion instead of x, v, and a. We also looked at how we use modified kinematic equations to actually solve problems and how that it's pretty similar to what we used to do. The only difference is that we can go back and forth between linear and angular, like the bike problem. We know how much this spun, and so then we can figure out how far we actually went with the wheel. Okay, and that is the end of this video. So I will see you on Monday and Tuesday, and we will do homework problems and go more into this idea of rotational motion.